And welcome back to experiment number 4. Lighting the LED when there's light, extinguishing when it's dark. So, experiment 3, let's convert it to experiment 4. To get the opposite LED operation of the experiment number 3, we just need to swap the LDR and the 10K about. But will this give us the correct operation? Let's see. So let's swap them around. So we undo the 10K, and swap them around. You may notice here is one of the new components. It is basically a break so that I can take the connection out of circuit if I want to. It doesn't want to go back in. Give it a wobble. It's gone back in. My little feet are not working as well as I'd hoped. Right, so that's turned it around. Let's put power on and see how it goes. Well, straight away the LED is lit. How are we going to get the LED to go off? Or is there a bad connection? We can find out if the connection's up top. We take that off, it goes out. So, is there too much brightness? Well, so when a circuit is not behaving as we'd expect, it's just about going out, but it's a bit difficult. We get the two things that we use for fault finding. One of them being the circuit diagram, what we're going to do, and the LED and the resistor of swap places, as Adam pointed out. I think it was Adam pointed out that they were different on the drawing as they were on the board, but they're in series, so it doesn't really matter which way round they go. But I've now changed it for, to be with the circuit. There's the LED, there's the resistor, so it's the same now. And of course we want to bring in a voltmeter, so we'll pop up the voltmeter. Right, we'll pop up the trusted DVM. It's a bit on the slant. Better. And we'll measure some voltages to see what's going on. So we'll clip that onto 0 volts, and we'll clip that onto the midpoint, and then we have 2.5 volts at this point. Let me bring our hand in. and we want that to go below about 0.6. It's getting down there, but you've really got to obliterate it out. So what we could do is just have a think about the circuit. Well, let's have a think about it. Let's break the circuit down into the bits of interest, which is these two. And what do we know? Well, the main part is we know that to turn the transistor on we need a VBE of about 0.6 volts across there, and we have a potential divider between here and here. So what sort of value do we need on here to produce 0.6 volt across there? Well, if you think about it, we got 10k, 0.6 volts across 10k is 60 microamps. And so we got 5 volts here, 0.6 here, we got 4.4 volts across the LDR. And 4.4 volts with 60 microamps flowing down here, and the LDR only needing to be about 77k to get the 60 microamps down here. That's not a lot of light. You know, it's getting close to being dark 77k. So that's going to limit how well we work. Now we could put a pot in here and just drag it up and down with a pot, but pots are expensive and you don't want to use pots if you don't have to. So what can we do? Do we increase this value or reduce it? If we increase the 10k, then the 0.6 volts across the higher value will mean less current. Less current means this this will be working easier. You know, instead of being a 77k required to pull the bass up, it might be 100k required to pull the bass up. So we don't want to go higher. So what happens if we decide, okay, then we'll reduce this to 1k? So we increase it down to 1k. Now we still have 0.6 volts across here, so we still have a 0.6 volts across here. But now we've got 0.6 volts divided by 1k, 600 microamps, 10 times more current, which also means that our value here is going to drop by 10 times. So instead of being around 77k, we're now going to be dropping down to about 7.7k, which means a lot more light has to fall on this to turn it on. So let's change the resistor over. Find the 1k. While we're at this point, I'll show you the new component that I made, which is basically, you saw it on the short, it's basically a connector like that with the middle pin taken out. And the idea of that is I can bridge it with a jumper, save me having to unplug things and that. I can just bridge the check connection with that, or I can remove the bridge, put it back where it was, and I can replace the bridge with a set of leads that I can plug into the multimeter and measure the current flowing through it. So that's what the new component does, if anyone asks. Right, we've gone to 1k. Power back on, and now we might need, you know, we don't have to get so close to pull it off. And also you can see on the on the voltmeter that we can go down below 0.6 relatively easy. If we take away some of the light, it'll probably be easier still, because you can see that I'm just moving the light bulb slightly to one side, and now you can see that, you know, it's dropping. But that gives us a clue, doesn't it, that that's having to work harder because there's more current going through it. So to turn it on, it's got to have a lower resistance, which means more light goes into it, so there's a bit more shielding, and it goes high enough for the 1K to pull the circuit down. So, just out of interest then, let's do a few measurements. So at full brightness like this, put a bit more light on it, we have, let's just turn it off. So now with the light on it, at this junction we have 1.47 volts. We'll bring that in, the voltage at that point. So what voltage have we got on the base? Well, I have 0.668. So we have 0.668 volts. So what can we work out from this? Well, if we know we have, can I bring my calculator in and will it read it? Can you see it there? Calculator over here maybe. To lift it up on something. So we have 1.47 minus 0.668. So we got 0.802 volts across the 10K. So if we divide that by 10K, we have, so that's our calculated current there. We have 1.47 across the 1K. So 1.47 divided by 1K, 1.4. So we'll bring that in and we'll stick it there, which means that we have the current flowing down here. If you use Kirchhoff's law, current flowing into here is the same as the current flowing out there and the current flowing out there. So the sum of the currents at that junction is 0. So if we add 1.74, 1.47 exponent minus 3 plus 80.2 exponent minus 6 equals 1.55 milliamps. And we'll bring that over there. So that's the current flowing down there. Now, what will we get if we actually measure it? Will it be anywhere near? So we can take that away. I'm going to turn the supply off while we plug this one in. It's always wise not to plug things in while the power's on. So we'll pull that one out. And plug that in. power back on. And the current is slowly creeping up. So what do we calculated it at 80.2, and I suppose if I've moved the meters, see, like, you know, I've only got to nudge something and the current changes, so slight changes and it all goes out. Well, there it is, like it's 80 there. So we'll settle with that. We'll put it in brackets so you can know it's a measured value. Right, then we'll turn power off again. We'll unplug that, plug that in, and we'll measure the current flowing down there. Power back on. And slowly let it settle. So some of this might be the charge building up through there and it settling itself out. If we say it's that's 1.463. So we'll bring that in, and that just leaves us with the last current to measure. I want to let it rise up. Oh, 1.55, so we'll bring that in. And that just goes to show, you know, with the currents there, how close the measured and the calculated from the voltage calculated from the voltages were to the actual measured values, and the fact that this one was calculated just by adding the 80 and the 1.47 together, and you know, it does show that is what's happening in practice. So if you like this style of, you know, experiment, you know, you like a bit more number crunching and a bit more, you know, what the circuit's doing, then you know, click on the subscribe button, click on the bell for notifications, and hit the like button if you like it. You know, at least YouTube will notice you more with lots of like buttons being hit. Anyway, with that said, I think this has put number 4 to bed, and I look forward to seeing you on number 5. Bye for now.